Hello viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about something very fundamental. Basically, how the heck we encode data into radio waves. What does these means like AM, FM, PM, what the hell they mean? So let's dive deep into it. So basically, we need wireless technology. It's fundamental requirement of human civilization. Be it ships, ships were earliest what you call long-range transmission, planes, trains, mobile phones, satellite. All of these things need it. It's not optional. It's compulsory. So there is that, and light has one of the unique advantage. For example, we did try to use ultrasound for communication. It's just that A, it's slow, B, it requires medium, meaning you can't send ultrasound from Earth to satellite. So radio waves travel at light speed, aka C, aka 300,000 km per second almost. So it's fast and it is able to traverse any medium. Meaning you do not have to, like if it's an electrical signal, you have to have a conductor like a copper. If it's a optical fiber signal, basically optical fiber laser light, it has to have a pipe which is optical fiber. Radio waves, it just goes through the air even in vacuum because it's a mediumless system. And it is fast. To give you a context, you can go to moon in 1.6 seconds. Our fastest rocket going YOLO speed, it still takes 3+ days. So yeah, it's fast. And if you are trying to circumvent the Earth, basically, let's say you are on the opposite eye, you're sending a call, receiving a call, that's 0.34 seconds. Like practically speaking, most of the time you will not have any latency because of the light speed, unless you're talking to moon. There it will be noticeable, but everywhere else it will be barely an inconvenience. So it is fast. And it has a lot of room for activities. For example, what we classify as radio or radio communications, that has 300 gigahertz of bandwidth. It's fat. Basically, it's a free for all. Go YOLO on it. So that created a problem. Like you can't just define a band that is that thick. For example, infrared band is huge, like bonkersly huge. So we had to define it as like, okay, near infrared, mid infrared, far infrared. So colors, again, we have millions of color in the same wavelength. Basically, colors are like this much and we have sliced it in millions of pieces. You can't do that with radio, like a radio is too fat. So we created a simple formula of base 10. Like on a radio level, that's what we use. So the idea is 3 kilohertz to 30 kilohertz would be classified as very low frequency. Then you add a 10 to it. Basically 30 kilohertz to 300 kilohertz, that will be 10 kilometer to 1 kilometer signal, that is low frequency. Then you go to 300 kilohertz to 3 megahertz. Now you are dealing with 1 kilometer signal wavelength, 200 meters. Basically in multiples of 10, you go from very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. Now let that be very clear, this is from a radio department. People, when they are using it, they might add extra name to it. For example, when you are talking about 3 gigahertz to 30 gigahertz, you will find a lot of extra names there, because again, they are designed in base 10, they're still fat. So they are like, okay, we are talking about X band, we are talking about Y band. That's what's happening inside the super high frequency band. I do not know why the heck we just accept it and just say what's the gigahertz, like 2.5 gigahertz, like your Wi-Fi, 5 gigahertz, like your Wi-Fi, 6 gigahertz, your future Wi-Fi, 7 gigahertz, some satellites. So again, it's huge band, so we had to, because be mindful, wavelength we are talking about 100 kilometer to 1 millimeter, and again at millimeter you reach that point where we call millimeter wave. So, and each of these bands, they are not just like, okay, for human understanding. These bands have different physical properties, as in some bands, you can send like, you know, almost to submarines. It can go that deep. It's like you can talk to submarines, specifically very low frequency. You can literally maintain a communication link with them. Then you have low frequency and all that. Like if you have a ship in middle of nowhere in, you know, Antarctica, you can still communicate to it. So as you keep changing the frequency, how Earth's atmosphere is behaving to it changes. For example, when we use a radio frequency AM system, which is medium frequency, these puppy bounce from Earth's atmosphere. Be mindful, only at night time. Daytime they will not bounce. No matter how much energy, as sun ionizes the upper layer, it does not bounce. But at night it bounces. So you can literally, like in my case, I am in India, I can hear China's radio, I can hear Europe's radio. Again, if I have good enough system, I will hear it. So it will bounce. Now that's a problem. If you want to talk to a satellite, you don't want atmosphere to bounce your signal back. So we have to go to a different band. Basically, super high frequency band, so we can punch through the atmosphere without any issue. Line of sight, direct working. So each of these bands have their own unique signature, and inside the band itself, for example, 3 gigahertz to 30 gigahertz, and again UHF to SHF band, you have 2.5 gigahertz, you have 5 gigahertz, and they both behave completely differently. So that's why we have so many bands. Like, this is a very free room to work with. Now we talk about amplitude modulation. Now we started wireless communication very early on. Once we figured out how to make radio waves, we are like, okay, ta-ta, ta-ta, ta-ta-ta-ta-ta. We literally were using telegram technology on it. Basically, we just replaced the copper wire with a wireless signal. It did work. However, it was not transmitting. It was just a beep or bops. Amplitude modulation, once modulation happened, meaning we had continuous variation on the signal. That is the oldest technology of human encoding. We take a carrier wave, whatever the frequency may be, let's say 500 kilohertz or 600 kilohertz. You take the carrier frequency, you overlap basically your input signal, be it digital data, be it a voice. We started with voice, and it will change the amplitude. Basically, for example, if you have an antenna there, it will go at the trough point, it will go to 3 volt, at a peak point, it will go to 5 volt. Basically, you are getting a signal, a low frequency signal overlapped on a high frequency carrier. Whenever you are talking about radio channels that are AM channels, you are talking specifically in 530 kilohertz to 1710 kilohertz. It's in kilohertz, so wavelengths are huge. And the basically gap between channels are generally have to be kept at 10 kilohertz. Now you might be like, okay, why do you need a gap when the signal is not shifting in frequency? It's one frequency going up and down. So why the heck this 10 kilohertz wiggle room? Well, this is where physics comes to bite you in the ass. So physics is like, you have a carrier signal, great. You overlapped any signal to it, human voice included. It will create what we call lower sideband and upper sideband. That is side effect. It's almost like how you have harmonics in electrical system. It will be created. No matter what you do, it will be created, and you always have to make sure the secondary channels that you have must be further away. It has to be. Otherwise, they will start to fight with each other and you will get interference. So that's why there is that much wiggle room. And this noise is directly proportional to how much change you are doing. If you're changing this a little bit, the sideband shrinks. If you're changing a lot, like whoa, 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 the upper band and sideband will expand. And that's why we teach trigonometry to children. This is the use of it. Trigonometry will tell you mathematically why this puppy happens. So mixing two radio signals basically creates a radio noise. Radio noise means you have to give some wide lane buffer booth, so to say. Now the best use of this technology right now, amplitude modulation, it's in air traffic control. Why? First, this modulation technique, I'm not talking about the frequency. You can change the frequency. For example, here we are talking about kilohertz. You can use 2 megahertz. You can use it in gigahertz. Modulation technique is independent of the carrier mode that you're using. So generally ATC has higher frequency, generally higher than what you call FM channels, higher than that, but modulation is amplitude modeling. Why? This has one unique ability. It allows you to overlap channels. For example, if 2 planes are coming in and both starts to have the radio setting to the same controller will hear both of them. Again, it will be overlapping, it will be noisy, but they will know that 2 people are trying to contact the same channel. And that is a very important thing, because worst case scenario is like, let's say a plane was near you, other plane set the radio signal and screaming mayday, mayday, mayday. You do not want to miss that. Under no circumstances you want to miss that. So this allows basically pilot A, pilot B and controller, all 3 will know something is going on if you overlap system, meaning they will not oops it, oh I forgot, or I did not hear that signal. Like radio wise, you will hear the signal. It's very distinct and it's shut up, take money kind of technology. So that's why air traffic controller, whenever you are hearing their video recordings, is like on YouTube and all that, it's like, why the audio quality is not that high? AM is not that high quality. Like physics wise, it's not high quality, but it does allow overlap. And because they are using higher frequency, it does not bounce from the atmosphere and go back, because worst case scenario is like you are hearing something from other airport. So they do want line of sight kind of scenario. So amplitude modulation is the basically encoding method, and frequency they select based on the requirement and weather conditions and all that. Now we come to the second technology. Now there was a technology in between, but we did not mature it enough. So FM technically is the second oldest technology. So the idea is, what if the wave itself was switching? For example, right now the old system is you are plotting it, basically what is the voltage going up and down on it. But what if you have reality, basically you have spark plug firing, you have lightning happening. What do they change? They change the amplitude. Either signally, basically that pulse gets added constructively, goes up, or shrunk by counter destructive interference. So you will always have a scenario where amplitude is being changed by noise in the environment, so you're not getting a clean signal. So somebody is like, what atmosphere will not change is the frequency. So if frequency is, let's say, 104 fever FM, so that 104 will not become 105 no matter what you do. The signal can expand or contract, but it cannot shift. So they're like, what if you shift it, and that's where you send the data? It's like, hey, so, shrinking and expanding, that's where my data is encoded. And that's the whole point. Basically, you're shifting the signal itself, the carrier itself. How do we do it? We realize oscillators, we let oscillator flex. So if oscillator is designed to run at, let's say, 105, we'll let it go to, like, little bit more, little bit less, little bit more, little bit less. How much more and less? You're talking about 75 kilohertz plus and minus. Again, when we are talking megahertz, so it still may find like a small thing, but it's a huge thing. Be mindful, we had band gap of 10 kilohertz. Here we have travel of 75 in one direction, 75 in the other direction. So you are talking about like huge band. We generally give 200 kilohertz of channel width. We have to give that much, otherwise it will interfere with something. Same thing, when you are changing something, it will create radio noise in the other area, sidebands. So 200 kilohertz becomes your buffer zone, so to say. It does not allow channel overlapping, meaning if two planes were using FM encoding, the one that has a clearer signal will be very clear. That's the good part. Bad part, the other part will be completely overlooked. It does not care about that. So, and it does have resiliency. We go through this because, again, when you are talking about something this much, like, hey, that's enough room to encode data. Yes, we encode stereo data. Like, this is the first time radios became stereo, meaning you can literally have podcasts, so to say, where it's like one person is in 1 year, another person in this year. That was possible. And we started with that. Where it's like, it was a mono because, again, 1930s. Then we are like, hey, what if we added a signal that tells that this is a stereo signal. Old radios will still work the mono signal, but the left and right data is on a different carrier. Basically, in that 75 band, it is there. It's just that newer receivers can read it, and they're like, okay. Then it's like somebody's like, what if we put digital data there? I'm talking FM, like, your city FM. They have what we call RDNA or something like that, that actually has data. So if you have a modern mobile phone, modern car radio, it will literally show you the channel name, assuming the channel is transmitting, or the song name. Like, you can actually see the text name of the song. So that's the whole benefit of having that sort of wide range and clarity. This thing does not get distorted. So again, amplitude will change because of interference, but signal is not in the amplitude. So that's why we use it. And again, this is how I downloaded satellite images back in the old days. NOAA satellites, I do not sure whether there's 3 of them are still alive or not, but this is how you can use NASA's satellite, old satellites, analog, ancient satellite. It's screaming in FM band, 137 megahertz, right? Yeah, 137 megahertz. Problem is, I removed all this system because I have an antenna that is like 108 megahertz. It's screaming, it's a FM. My 3-story tall antenna, that's 3-story tall, it's overlapping the signal. It's like, it's frustrating. And again, because it's in sun synchronous orbit, it's always in the evening. If the satellite was going overnight, FM shuts off at night, I will get clear signal, but it's like, it's overlapping. Again, this is screaming so loudly, the SDR is like, bro, like, again, interference is not happening, that's why I can get the whole picture, but FM does have that sort of issue where it's like, if something is screaming too close to you, interference suppression also has a limit. So that's why we use FM whenever you have to communicate something. Meaning the first satellites we sent, we were relying on FM technology, not AM technology. Because again, going through the atmosphere that much is like lol. AM will become lol. Lightning happened, lol. Then we come to the most complex black magic. It's like, what if you change the phase? And it's like, what does that mean? Smaller cousin of FM. Basically, you have a wave, right? So everything that we have done so far, AM and FM, they are basically how high the waves are or how far apart they are. Okay. What if you chopped it up? What is like, okay, wave, Basically, you take one cycle and you chopped it up in that cycle. Basically, you're like, no, no, no. What if I cycle it here? What if I cycle it here? It's like you get these V and W, those sort of systems. So it's like these sort of chopping that is happening inside a wave. That's phase modulation. Now, like this was the second technology humanity figured out before we did FM. The early days people did not like this because this was mathematically they thought this will create way too much what you call recoil damage, as in like the spectrum requirement would be bonkersly huge. Although that turns out to be not true if you are smart with it. So inside a cycle, basically you're taking a single wave and you're changing it, not just like, okay, count how many waves, like, you know, how far apart they are, how amplitude is there. It's just like inside a wave you're detecting it. So how the heck we did that? Like, again, now it's a basic stuff, but how the heck back in the days, 1930s, we did that? Constructive and destructive interference, meaning you sent AC signal, which is the waves, and you had one offset by a capacitor. Merge them properly based on your impedance, basically input, and voila, you will get your right chopping, constructive interference and destructive interference. And that's how we started phase direction. And somebody in 1960s figured out, hey, wait a minute, we have AM or FM. Let's just assume we take AM, your amplitude change. Well, the phase data still would be there. Okay, what if we did FM? Phase data still would be there. So somebody figured out that utilizing the mathematics of sine and cosine, you can have two data stream on one wavelength. Let that sink in. Two channels, physically, continuously analog channel, can be transmitted on same transmitter, received by a same receiver on one spectrum, as in like one wavelength, and voila, you have two data out of it. That's what we call IQ component. You keep hearing about IQ component, that's what it is. Basically the fact that you are like changing your sampling point. Basically you are sampling, normally sampling, FM sampling, and then you have like, okay, wave tip was detected, 90-degree offset. You detected 90-degree offset, cosine, and you plot that data, and voila, somebody figured out now we can have double data. This is when I used to download from Russian satellite, which was 137 megahertz. This puppy, you will see this quadrature data point. Yeah, it is what we call double data rate, meaning instead of sending on or off like 0 or 1, it is sending 0, 0, 0, 1, 1, 1 or 0, 1. So it has 4. Basically every pulse is double dipping. By the way, your computer also does the same thing, and this is the old technology. I'm pretty sure this satellite was launched in the 80s, so I'm not sure whether it's still alive. It did have dead pixels. So that's how we send double dipping. That's how your Wi-Fi works. That's why you can, in principle, nowadays you can look into a system. It's like, okay, 1 Gbps of Wi-Fi data. How? Well, this 4 points, yeah, somebody figured out like if you have good enough analog to digital sensors, good enough signal to noise ratio, you can have bonkers number of points. Like you can go from 4 to 8 to 16 to somebody's like, okay, what if we have 4,000? Not even joking, it actually is something there. 4,000 symbols in one pulse. Like I talked about, like you're double dipping. It's like, what if you send the whole bit, not bit, byte, whole byte in one pulse. Byte, you got the whole byte, whole. So that's the whole point, because we figured out sine and cosine allows you to what we call in phase and quadrature. And again, if you have remembered why the heck there is math and imaginary math or imaginary numbers, that's because signal is in phase, that is a real number, but quadrature you are extracting by offsetting it. So that's what we call imaginary number. So and it's the foundation. So you take data encoding either AM or FM, and then you do phase modulation on those, and then voila, now you have two data stream. And that's the foundation of every digital transmission that we are talking about. So this is the foundation. And be mindful, we generally do not do FM on it. The reason is, when you are doing this sort of harsh chopping, it creates way too much recoil damage. FM already is very sloppy, so you will always hear a PAM, so to say, PAM system, phase modulation amplitude. Reason is that amplitude is less what you call scattery, it does not eat up the whole bandwidth. Because again, 5 gigahertz is just 5 gigahertz. You go too much, you go into 6. 6 is illegal in many places. So for bandwidth efficiency, people generally use amplitude changing as one data vector and phase modulation as second data vector. Some mathematically have tried to have all three: phase modulation, frequency modulation, and what you call phase modulation. And apparently it was so useless. It was cheaper to have multiple antennas. That's why your modern Wi-Fi's have three or four antennas. It's like we send different data streams on multiple channels is much cheaper and better. So this is phase modulation. Now let's understand the future here. Radio encoding is core to human technology. As we evolved, our ability to dump data into radios evolved, and voila, you can see it. So for example, the best example of this sort of technology is MRI machines. Like, okay, why the heck I'm talking about radio in MRI? What do you think your body is screaming? Radio. Literally, that permanent big magnet that we have, that is running on superconductor 1.5 Tesla, that is quieting it down, forcing every single hydrogen in your body to align. It's basically suppressing white noise. It's like, nope, all of you align one. Then you have Z coil. Z coil goes, it selects basically where it is, like selects is where it is. You selected it, like slip disk mic, selected it here. Then you have X coil going from here to here. It's like it creates high intensity here and mild intensity here. So you get a frequency change. Yes, it's in frequency. 1.5 Tesla coil systems generally require 60 megahertz. So it would be like 59 megahertz here, 61 megahertz here. That's how you're changing the frequency. And then like, okay, that gives you X, Y, but three-dimensional data, and not to mention you have to see inside human body. So then you have Z coil that is going from your nose to this, that goes in pulse. So it creates a pulse, okay. So that you created basically a spreadsheet, but what the hell you gonna feed in the spreadsheet? There comes the phase modulation. Basically, when you based on how much hydrogen concentration you have in your tissues, in your bones, they react differently. Their phase are different. Phase becomes the data stream, and the antenna is now getting two data stream, basically where it is and how bright this pixel is supposed to be. And voila, this go into what we call K space mathematically. And like, isn't that just one amplitude? Yes, that's the magic of Fourier transform. And voila, basically this is a super advanced radio. As our radio technology became, MRI became better. So you take a super duper big magnet and have three gradient coils and go YOLO on it. Although I'm still not sure why the heck we don't have multiple Z coils. It's like, have multiple different radios, like, okay, 65.00, okay, what if 66? It's like, have a different SDR. Again, I understood in 70s, but like nowadays we can afford SDR, man, come on. So software defined radio is the same thing of radio, but somebody's like, okay, what if we apply Fourier transform on a whole wavelength? So you are mapping the amplitude, but again, that's all you have, amplitude, but you have a bit depth, as in your analog to digital converter could be 14 bits. So it has 14-bit value where the amplitude was. Map it over time, apply Fourier transform, ta-da! Basically, these puppies are creepy when you actually first use it, is that if you have living in a town, it can parallelly listen to all the channels, all of it. It is creepy. Like first time when I experienced it, like, wait a minute, you are telling me that I can listen to this and that, all of it? Yes, yes. The answer is yes. And if you're like, okay, what do those surveillance plane, military analysts, that's what they have, SDR. They just record everything. So once they record everything, then the analyst will sit down and scan every single spectrum or run an AI through it. So again, it's black magic technology. It's like, again, Fourier transform is the black magic, and it's the creepy part that somebody figured it out in the 1800s. So satellite comms, when I started that Russian system, it was like, okay, 4 data points. Modern systems that have dish and all that is like, yeah, that was easy. 128 bits. 128 symbols are there. You have to figure it out. And you're like, okay, how the heck you get 2 data points? Basically, like in MRI scenario, you take carrier signal, you send it into your one frequency system, and then offset it by 90 degrees. Basically, this has to be offset by 90 degrees. Second sampling point, and that will be created into data point, what we call adder. And like, okay, you must remember we taught you graphs and numbers and imaginary number. Real signal becomes your real number, and the 90-degree offset becomes imaginary number. Now you create a what you call coordinate system. Now you have the data points. Enjoy. Again, if this video gets a good traction, I'll go dive deeper into the digital encoding black magic that we do. So it's on a whole different level. again, understand that, like, we have the ability right now, you can just buy it, where it's like, okay, I'm hearing the whole goddamn spectrum, meaning if you want, you can easily, I'm not talking like spending bonkers amount of money, easily buy a system that where it's like, yeah, I'm listening to every single FM channel right now. You can, including if you are near to airport, you can listen to it. You can listen to all airplanes legally. You just can't transmit. Thou shall not transmit. Listen, go YOLO on it. So that is there. And the magical part is all of it is just amplitude change over time. Nothing else is changing. It's just that if you have a conductor is getting more energy or less energy. There is nothing else, but we are packing everything and Tom, Dick and Harry into it. So that's the interesting feature. And I'm like, somebody will figure out how to do that 3-axis transmission effectively. But damn, that would be like, damn, we'll have like, oh, I only have 10 Gbps on my mobile phone, Wi-Fi. So this was my presentation on basically the black magic of radio data encryption. Hopefully you have liked it, learned from it. In that case, please give the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excitement. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and if you have enjoyed it, click the like button. Thank you.